Hello. Good afternoon. I'm Zach Papiez. I'm joined by my colleague, Imburgia, and we're here representing Magnalytix. Our focus today is on two-phase system performance, utilizing distillation to remove contaminants and improve reliability. Distillation is often used to purify solvents like those used in two-phase solvent or two-phase cooling. We wanted to capture this idea and how it applies to hardware operation. Oh.
So a brief background on who we are at Magnalytix. We operate a surface installation resistance test lab serving high reliability electronics manufacturers. If you're unfamiliar with surface installation resistance, very quickly, it's the measurement of very low current on the surface of a board between conductors of opposite polarity. And it's used to qualify the electrochemical reliability of production hardware. We do this because process residues, if they're left on a board and that board is exposed to challenging operating conditions, it can lead to expensive hardware failure from events like corrosion, electrochemical migration, and dendritic growth. So when we aren't assisting customers qualifying their manufacturing processes, we're involved in all different kinds of research within the realm of electronics reliability. And one of the avenues we've spent a good deal of time researching is that of environmentally based electrochemical failures like the ones that we see in high resistance dielectric fluids.
So we have a deep background qualifying process residues on printed circuit board assemblies and their resultant electrochemical failures in air environments, and similar mechanisms can occur in two-phase fluids. So they have the potential to extract in various additives and with boiling deposit them under the surface of critical components in your hardware. So here you can see pictured electrochemical migration occurring in both air and in two-phase immersion coolants. To take these images, we utilize faux components made of borosilicate glass that had copper pads screened onto them that allowed for us to mount them on our PCB coupons in a manner that resembles hardware assembly. You can see the metallic filaments growing between the conductors of opposite polarity in both examples. In air, this is made possible through electrical bias, humidity, and process contamination. But as mentioned, in two-phase fluid, there is the added potential for contaminant building up over time. And we call this global contamination.
So as Zach just mentioned, two-phase immersion fluids can act as a weak solvent that over time can extract problematic residues into the fluid. This fluid tends to deposit itself in areas of the board that are exposed to high heat from boiling action from high-powered heat generating components. Once it's deposited, it takes the form of a goo or a gel-like consistency that when examined with FTIR analysis, it's composed primarily of polymeric compounds like plasticizers extracted from submerged hardware and flux residue from the assembly process. And the image that you see here is some of this deposited residue on one of the comb patterns of a test card that we used for immersion testing in contaminated fluid, and this was after just a week of testing.
So here's a quick example of one of our coupons tested in immersion. You can see the after image shows that clear evidence of deposited residue at a very low contamination level, just around 20 parts per million. We also charted surface installation resistance over the course of this test. That green line there represents the component. You can see that there was a sharp decline in resistance and then a slow decline into that red shaded region. We use that decline in resistance as evidence that some conductive residue has appeared on the measured surface of the board. The two lines at the top there that did not change or actually represent portions of the board that we did not observe deposited residue.
So two-phase fluids They're great for heat removal, but they also have the tendency for material compatibility issues that must be addressed for long-term reliability, particularly in high-consumption data centers. The reduction in fluid performance the means of combating this contamination is with constant filtration with activated carbon. And these carbon filters, they're designed to absorb organic contaminants like flux residues, oils, and plasticizers, like the ones that we identified in the FTIR analysis. But the problem with these filters is that they have a limited lifespan due to a variety of complex factors like contaminant load, the operating conditions, and the potential for moisture ingress. And this is a dynamic process, so it's kind of hard to identify or establish systematic maintenance. So regular monitoring is required to avoid overload in your filter. And if your filter does happen to get overloaded, it could cause the breakthrough of contaminants back into the fluid. Also, depending on the contamination, it could require multiple filter changeovers, which could lead to an appreciable fluid loss over time. So it was with these limitations in mind that we asked the question if there was some other means of fluid purification that could assist in this current filter process.
Yeah, so like Matt was saying, we asked if these are already recycled in bulk commonly, that can we take a proactive approach to filter the fluid while the system operates? If we can remove them as they appear, perhaps we can extend intervals between carbon filter changes and add another line of defense to your system. To demonstrate this, we utilize two complementary approaches, gas chromatography to measure the fluid purity over time, as well as simulated or electrical test vehicles using surface insulation resistance to track to simulate the hardware over time while running closed loop distillation. We opted to take multiple samples of gas chromatography over the course of testing, so a baseline in the 3-gallon test tank at GC1, doped the tank at roughly 200 parts per million, allowed to mix for 30 minutes, and sampled again at GC2, and then initiated the closed loop distillation and took samples at 1 hour, 24 hours, and 48 hours.
So the immersion vehicle that we used is based on the surrogate test cards that we use for our traditional SIR testing. We realized that with some modification, this test vehicle could be used to model real-world risk in two-phase immersion fluids. The test card consists of a series of interdigitated comb patterns that provide us with the low current, high resistance readings that we use for our SIR measurements. And then electrically inactive dummy components of specific sizes, attachment schema, and standoff heights are used to mimic production components. We embedded a heating element within the layers of the PCB to facilitate the boiling action of high power, high compute components. It was with these all of these elements combined that we were able to facilitate or create a reliable facsimile of the dynamic interactions of dielectric fluid with an equivalent component type. And for our tank setup, we used a series of stainless steel sanitary fittings that consisted of a large sight glass for our main test tank, and it had an integrated cooling coil, a smaller sight glass with a 200-watt heater to facilitate the boiling, and we had a series of connections to provide a closed-loop circulation of the fluid between the two chambers. In the main test tank, we also connected our test vehicle to a edge connector to provide us with the resistance values and the edge connector also provided heat to create that boiling action to simulate production hardware. Once we contaminated the tank with a DOTP contaminant, a stir bar in the main test tank provided a homogeneous mixture of the fluid, and that fluid is then gravity fed into the boil chamber where the contaminants are collected and the purified vapor is then condensed back into the test tank.
So like we mentioned before, it was we opted to dope the tank around 200 parts per million. We chose a known plasticizer to do this, DOTP, but as plasticizers are known to be leachable and potentially failure-causing in two-phase fluids. When the contaminant was added, there was an immediate response from the resistance values. The BGA and QFP components, channels 2 and 3 respectively, responded much more drastically. It's likely that the larger surface area of these components played a role in this. When the distillation was initiated, some of the resistance values recovered while some merely stabilized. It's likely that some contaminants were left under those component packages at the end of testing. So, similarly, the GC values dropped pretty precipitously. At the beginning, it was roughly 200 parts per million and quickly fell to under 2 ppm in under 2 hours, which was quite close to the virgin sample measured directly out of the pail.
So the conclusions that we drew from this testing is that by integrating a closed-loop distillation system into the tank of an actively cooling two-phase fluid, it was indeed possible to reduce soluble contaminants from hundreds of ppm down to near virgin levels, which was measured by our gas chromatography analysis. The 200-watt heater created a distillation rate that was pretty close to what we were expecting to see from our theoretical distillation rate, and the fluid purity stabilized between 1 and 2 ppm. We also observed that the SIR measurements responded immediately to the addition of the contaminants in the tank, and they only partially responded to the cleaning of the fluid. So it is possible that it requires a longer exposure to the clean fluid in the tank to disperse the residues and recover the resistance data, or it's possible some other cleaning protocol may be required. Also, we would like to note that the 200-watt heater in the boil tank probably isn't sufficient to cool or purify the fluid in a much larger tank within the same time period, but hopefully the takeaway is that it is indeed possible to purify a fluid while it is in operation.
So in a quick few planned community contributions that we plan to publish a full paper surrounding this information, as well as offering readiness consultations for OCP members. We also plan to submit Magnalytix test services, components, and systems on the OCP marketplace.
And finally, to wrap up for our call to action, we just wanted to demonstrate that these ideas were working, but we also want to collaborate more closely with the industry to integrate these methods into two-phase immersion tank setups. We do have ongoing work with the Material Compatibility Subcommittee to ensure that these ideas are effective and scalable. And while this testing was exclusively for two-phase immersion fluids, we are also working with single-phase fluid manufacturers to better manage and monitor contamination and fluid aging. And finally, we'd like to offer special thanks to Steve Pignato and Standard Fluids for generously providing this fluid that made this test possible.
All right, any questions?
Thank you for the presentation, guys. One question I have is, when you show it reaching a purification level, what happens when you run it beyond the 48 hours test? Does it just maintain purity indefinitely?
You say the components that, like, when it's stabilized out. So the ones that reduce contamination or reduce resistance like that, we could expect some of them will continue to go down. Let's say at some point there might be some ECM event that would cause it to reach the floor of what you're measuring. But if it was never contaminated in the first place, and it was continually cleaned, we would expect it to stay stable throughout.
How you guys doing? Good presentation. Just a quick question for you. What chemistry were you using with this testing?
This was used with Novak 649.
Thank you. How would you characterize it for different chemistries? Have you looked at, like 649, for example, is a fluoroketone. Hydrofluoroethers would have different, I would say, results versus other types of chemistries. So how are you looking at that, and do you plan on doing additional testing?
We do plan to do additional testing, and we have done some testing with a few different fluids, I think, that would match the ones you're describing. We've seen similar results, I'd say, from the resistance values on the bores with the same test setup.
Thank you.
All right, is that it? Cool.
Thank you.
Hello, folks. We've reached the end of the immersion track.
Yes, and also the end of the day for the OCP Global Summit.
Oh,
So-
and the end of the summit.
And the end of the summit. So thank you so much. So I want to say thank you to all the presenters, and also want to say thank you for all of you that are still here hanging out with us until the end of this session. So thank you so
Go ahead.
much.
Applause for yourself.